Rate determining steps, the speed bumps of chemical reactions. Don't worry, I'm slowly getting over them. That's right, today we're talking about chemical kinetics. Hit the theme!
Ain't nothing but a chem thing, baby. Two flipped out teachers going crazy. Lancaster is a district that pays me. Unbreakable, so please don't try to break this. But back to the lecture at hand.
Hello and welcome to another episode of SchuFu coming at ya. I'm your host Fu, and with me as always is Shu.
Shu know it.
So Shu, we're starting a brand new unit today, and we begin with the speed of chemical reactions.
Yeah, we call that chemical kinetics. So let's hurry up and get started. Chemical kinetics, a lesson from the kinetics and equilibrium unit. What are kinetics? Chemical kinetics deal with the rates of chemical reactions and the mechanisms by which they occur.
Let's begin with rate, the speed of a chemical reaction. When we measure the speed of a car, we measure the distance traveled per unit time, miles per hour or mph. Reactants get used up per unit time and products are created per unit time. When we measure the speed of a reaction, we measure the change in molarity per unit time, or molar per second. Note, a high reaction rate means that the reaction takes a short amount of time.
Let's talk next about the mechanism. A chemical equation only shows us snapshots of the reactants and products, but there are steps that occur in between. The mechanism is the series of steps that must be taken to reach the final products.
So if you take a look at the image of our client Bromeo Smith, he belongs to the SchuFu follicle regeneration formula program. He uses the product Brogaine. Now, all you see of Bromeo is what happened to him at 8 a.m. and 8 p.m. You don't see what happened at 2 or 3 in the afternoon. You only see before and after. Now, this is much like a chemical reaction where you only see the reactants and the products. You don't see what happened in between. Now, in a chemical reaction, all that stuff that happened in between, we call that the reaction mechanism. We're going to take a look at an example of a mechanism. Given the following chemical equation, OH- plus C2H5Br yields C2H5OH plus Br-. If we take a look at the image of this chemical reaction, we can see the reactants, OH- and the C2H5Br on the left. Now in the middle is what you don't typically see in a chemical reaction. This is the mechanism. It's in brackets, and as you can see, that OH- is beginning to bond with that central carbon atom, and the Br is starting to unbond from that central carbon atom. So then we get our products of the C2H5OH, and the Br- is now separate. Notice how there is an intermediate product that exists between the reactants and final products. This is called the transition state, or activated complex.
The activated complex often involves all species combined together. This gives it a very high energy, making it very unstable. This leads to it only lasting for a short amount of time, making it difficult to observe.
Taking a look at our chemical comic strip, we have on the left reactant particles approaching each other. In the middle, they collide and form the activated complex. And on the right, they are product particles that are flying away. The greater the number of steps and the greater the complexity of the mechanism, the lower the reaction rate.
If we take a look at the images below, we're going to use obstacle courses as an analogy for chemical reactions. Both obstacle courses and chemical reactions have a start, a finish, and a series of steps that occur in between. If we look at the image on the left, we have a very simple, inflatable obstacle course for little kids. Now you can get through this pretty quickly. There's not a lot of steps, they're not very complex, and so because you can get through it quickly, this equates to a high reaction rate. It doesn't take a lot of time. If we look at the obstacle course on the right, this one has a lot of steps, they're more complex, it's gonna take a lot of time to get through this one. So this is gonna mean that we have a very low reaction rate because of it taking so much time to complete. So Fu, you wanna play with toys?
Yeah.
All right, let's have a marble race.
Okay.
Okay, so what we're gonna do is on 3, we're gonna hit this button and release the marbles.
Okay.
All right?
All right.
Okay, let's see who wins.
Okay.
All right, 1, 2, 3.
Oh, come on.
Woo!
Like all of yours got there first.
Yeah.
Come on, your course is like way shorter. You look at this like little short ramp here. I got to go through all this twisty stuff. You were gonna win from the start.
Well, you know, it is kind of like a chemical reaction. I mean, if you think of this as a reaction mechanism, my mechanism was just a lot simpler than yours, and so I had a faster rate.
Oh.
The slowest step in a reaction is called the rate determining step. Because this step limits all subsequent steps, it determines the overall reaction rate.
We're going to take a look at a couple of images that illustrate a rate determining step. If we take a look at the image on the left, we have a traffic jam. Now the traffic jam is caused by a bottleneck or an accident, but we can only go as fast in that traffic jam as the cars that are going past that bottleneck. So our rate is determined by the step that's still ahead of us, so we're all slowed down. But once you get past that bottleneck, you're free to go as fast as you're able to, right? If you take a look at the assembly line on the right, we can only move as fast as the worker in front of us. Now, I know that I'm a fast worker, but this guy over here, he's slow and he's right in front of me. So as fast and as good a worker as I am, I can only go as fast as this guy. All right, one more analogy. When you're leaving chemistry class and you're going to your next class, do you ever have a freshman walk in front of you? You can only go as fast as that freshman is going in front of you. They're slowing you down. That's also a rate determining step.
It's time for
Invisible table talk. Shu, let's make sure we've invoked the spirit of the invisible table.
Okay.
It worked. All right, remember that time we got angry at our students for not knowing that .030 was 2 sig figs?
I remember that day. Wow, we were so angry. We went into the stock room, we found some plastic stock bottles, and we just ripped them all in half.
We did. We ripped 8 of them in half, but then we realized we have the perfect parts to make a great demo to show a reaction mechanism.
Yeah, we made reaction mechanisms. I did 1, you did 2, and they each have 4 steps.
They do. And we're going to take our reactants and we're going to end up pouring them through our reaction mechanism to, in the bottom, get products.
Okay, that sounds good. So I think what you're saying is this is another race that we're having?
Sure is.
All right, let's see who wins.
All right.
Ready, set, go.
Oh, I think I got you.
Oh no. Mine's going pretty good.
I had to stop pouring.
Haha.
Oh, I'm all poured. Yeah.
I'm all poured now.
Look, you got 2 really slow steps. I only got 1.
We shall see.
But
I win again! This is awesome. Way to finish the race. You try number 1 from the funnel demo. Which funnel mechanism had the fastest rate? Explain. Which step in funnel mechanism number 2 was rate determining? Explain.
so which factors affect reaction rate? Reacting particles need to have effective collisions in order for the reaction to occur. An effective collision involves proper energy and proper orientation. Remember?
Oh, I remember.
Wait, what?
Any factor that increases the number of effective collisions increases the reaction rate.
To better illustrate collision theory, let's take a look at the image on the right. If we look at the first example, we see two molecules colliding with the correct orientation and sufficient energy. This leads to an effective collision and a reaction occurs. If we look at the middle example, there's no reaction, and this is because the two molecules are colliding at the wrong orientation. Finally, in the last example, we also have no reaction because the two molecules may be colliding with the correct orientation, but they're colliding with insufficient energy. The first factor that affects the reaction rate is the nature of reactants. Generally, ionic compounds in aqueous solution react more quickly than molecular compounds. Molecular compounds tend to contain many covalent bonds to break and then reform as products, which leads to slower reactions. Ionic compounds in aqueous solution are freely moving and available to have effective collisions, which leads to faster reactions.
If we take a look at the image to the right, we have two beakers full of two ionic solutions. Both those ionic solutions, obviously they're all dissolved, they're dissociated. Those ions are free to move and free to collide. Now, when we look at the second image, we have Bromeo Smith, our lab assistant, coming in and pouring the two solutions together. Now, the moment the two solutions touch, almost instantly those particles are ready to collide. And when they collide, they have a reaction. They're actually forming a precipitate. This is a precipitation reaction. That yellow substance that's forming there is our precipitate. And as you can see far to the right, we have fully formed precipitate and it's settled to the bottom. Concentration. A greater solution concentration, molarity, means that there are more reactant particles available to react. This increases the frequency of collisions, which increases the reaction rate. To further show how concentration affects reaction rate, I like to use the analogy of country roads versus the highway. Now, on the highway or the thruway, you have lots of cars, so there's a high concentration of cars. So the likelihood of there being an auto collision is much higher, so you have a lot more collisions on something like a thruway or a highway. Now on a country road, there's not a lot of cars, so the chance of you bumping into another car are much lower than they would be if you were on the highway.
Welcome to Floating Head Table Talk. We just got done talking about how concentration can speed up a chemical reaction. So we're going to show you that in a demonstration. We're going to react magnesium with hydrochloric acid. On the left, we have 0.1 molar HCl. On the right, we have 3.0 molar HCl. We also have 2 pieces of magnesium, and we have 2 forceps. Release the magnesium. As you can see, the reaction on the right with the 3.0 molar is reacting more vigorously and quicker. And done. 3.0 molar, a higher concentration, reacts at a faster rate.
Our next factor is temperature. An increase in temperature increases the energy of the reactant particles. This increases the frequency and energy of collisions, which increases the reaction rate.
So if you recall, temperature is average kinetic energy, and kinetic energy is the energy of motion. So really we're dealing with the motion of these reactant particles here. So as we increase the temperature, we're increasing that motion, which provides more collisions, and not just more frequent collisions. Because they're moving faster, they're allowed to collide with more energy, which passes that threshold of that minimum requirement for an effective collision. Another factor that affects the rate of a chemical reaction is surface area. An increase in surface area increases the number of reactant particles exposed. This increases the frequency of collisions, which increases the rate.
If we take a look at our image, we can increase the surface area of a solid by breaking it into smaller pieces. Maybe we crush it up. Now it may be a little counterintuitive that that's increasing the surface area, but when you break it into smaller particles, you actually have more of the reactant exposed for potential collisions. Therefore, if we increase the surface area, there are more possible collisions and the reaction rate goes up. Our next factor is pressure. An increase in external pressure on a gas forces the reacting particles together. This increases the frequency of collisions, which increases the reaction rate.
Taking a look at our image, we have a movable piston above a gas. If we push that piston down, we are pushing those gas particles closer and closer together. This is effectively increasing the concentration. It's giving you a lot more particles in a smaller space. What this does is it increases the amount of collisions you'll have overall, and since you have more collisions, the likelihood of an effective collision goes up, therefore our reaction rate would also go up. Our final factor affecting a chemical reaction rate is a catalyst. A catalyst alters the mechanism of a reaction by creating an alternate pathway. A catalyst is not consumed in the reaction. This new pathway requires less energy for an effective collision. Thus, the activation energy, or the minimum energy needed to start the reaction, is lower. This increases the number of effective collisions and the reaction rate increases. So before this school year, you probably already knew what a catalyst was and what it did. We already knew that catalysts sped up chemical reactions. What you maybe didn't know was how it sped up a chemical reaction. It does it in two ways, and we really need you to know these two ways. It lowers the activation energy, so it takes less energy to get from reactants to products. It also changes the pathway, so the mechanism changes. All right, so a good analogy for this is like going from your chemistry room to the field house for phys ed, right? So you start in the S wing, you leave your chemistry class, you make a right. You go down to the back hallway, you make a left, you go all the way past senior hall, past the music rooms, you make a quick left and a quick right, and you go down to the hallway for the field house, you make the right, and you go straight back, right? That's your pathway, that's your mechanism. If we were to catalyze this pathway and we were to alter it so it takes less energy and change the pathway, we might open the doors behind senior hall. So instead of going past the music rooms, you actually go out the back door and you go right across the grass to the field house. Now you still started in the S wing and you still ended in the field house. So where you started and end did not change. But what did change is your pathway, and it took less energy to do it. That's how a catalyst works.
And we're back.
With invisible table talk.
So Fu, you remember how every time we do one of these little reaction mechanism competitions, you always lose and I always win?
I know it all too well.
Well, you know, I was feeling sorry for you. So I decided I'm gonna let you do a catalyzed version of the reaction, and I'm gonna keep the normal uncatalyzed version of the reaction.
Okay, I see what you did here. A catalyst speeds up a chemical reaction by changing the mechanism, changing the reaction pathway. And we took out one of the steps of mine, so mine should go faster.
Yep, and I still have the original 4, so let's see if it helps.
All right, I'm feeling good about this.
Let's grab our reactants.
Okay.
Ready, set, go. Pour it all mine.
Okay. Looking good.
Close, close. I think I won.
I think by a little bit, yeah. You won.
It was close.
It was. Mine definitely went faster, that's for sure.
It did. But at the end of the day, I'm still the reigning champion.
You try number 2. An experiment involving the reaction of HCl aqueous and CaCO3 solid was carried out to determine how different factors affect reaction rate. In experiment 1, which beaker will have the higher reaction rate? Explain in terms of collision theory. In experiment 2, which beaker will have the higher reaction rate? Again, explain in terms of collision theory. Well, that's going to do it for today's episode on Chemical Kinetics.
It's been emotional.
Today's episode is brought to you by Big Brain GameWorks.
Majestic Moon Jigsaw Puzzle, featuring 12,000 machine-cut quarter-inch pieces. Magnifying glass and tweezer included. Decades of fun.
But we never off, always on till the break of dawn. SCIENCE in the hall they call S-Wing. You know we never wear a tie, like my homies, boys to men, it's so hard to say goodbye.
Like this, that, and this, and it's like that, and like this, and like that, and it's like this.
You're going in low power mode.
Plug and chill to the next episode.